Today we're going to take a look at a special type of probability problem called a binomial probability. So that's what we're doing. We are calculating binomial probabilities. And before we really get into defining what a binomial probability is and how it works, I want to take a look at an example that kind of sets up the thought process behind it. Let's say I have a baseball player who has a batting average of 2,700. Or 270, sorry. Batting average of 270 means he gets a hit 0.270 of the time. 270 out of 1,000 at-bats, he'll get a hit. That's the probability he gets a hit. I want to know, what is the probability the player gets a hit three out of the next 5 at-bats. And to kind of set this up, we're going to break this down into pieces. The first piece is the probability that he gets a hit. Now we can see just from the problem, his batting average of 0.27. That's the probability he actually gets a hit. And so we want that to happen 3 times. We want 3 hits. But we also want 3 out of the 5. That means there are 2 non-hits, right? Whether they're walks or strikeouts. So we need the probability of no hit. If he's going to get a hit 0.27 of the time, the complement would be a no hit. We just subtract 1 minus 0.27 to get 0.73 is the probability that he does not get a hit. And so what we're really looking for is we want to get the probability of 3 hits and 2 non-hits. Well, the 3 hits are going to give us a probability of 0.27, and the multiplication rule tells us we just multiply those together. We can do that because they are independent events. Getting a hit today does not affect his hit percentage tomorrow. So they're independent, so we can just multiply the individual probabilities. Then we've got the 2 non-hits, which are also independent, assuming that the batting average stays consistent. So his non-hits with a 73 probability. And that would tell us the probability he gets a hit, a hit, a hit, a miss, a miss. But that's not really what the problem is asking us to find. The problem says that the order does not matter. We just want 3 out of the next 5 at-bats to be hits, which means we could have a hit, miss, hit, miss, hit. We could have a hit, hit, miss, miss, hit. The order doesn't matter. And so to account for all the different orders and all the different arrangements, we have, as you would expect, a combination. There are 5 at-bats, and we're going to choose 3 of them to be a hit. So we're going to continue multiplying. So we're going to multiply 5 choose 3 times the 0.27. There were 3 of them, so I'm going to say to the 3rd power. And then misses, there were 0.73 to the 2nd power. This expression then will tell us the probability that we have 3 out of the next 5 at-bats will be hits. Pulling up the calculator to actually calculate that. Move the calculator over so I can see the problem. 5, math, over to probability. We're going to go NCR. 5, choose 3, times 0.27 to the third power, getting out of the exponent, times 0.73 to the second power. And we end up with a 0.1049. 0.1049. That is the probability that he gets a hit in 3 out of the next 5 at-bats. This example that we just took a look at illustrates what is called a binomial probability. The idea between a binomial, by the prefix means 2. The binomial probabilities have 2 options. The only 2 options are success, which we represented in blue, or failure, which we represented in green. And really, these should be put in quotes, success and failure, because success isn't always a good thing. A lot of the times in binomial probabilities, we're looking at defective parts, and the defective parts are considered the success, which isn't a good thing to have a defective part. So we use those terms loosely. Success does not necessarily mean a good thing. It did for our baseball player, but it won't always. Success is just the thing we're looking for. If we're looking for defects, defects are the success, and the good parts are the failures, just to make it nice and confusing. Another thing that's important in these binomial probabilities, for that multiplication of individual probabilities to work, they have to be independent. Independent trials, and you remember that means one outcome does not affect the next. Related to that independence is that the probability of that success is not going to change. We'll say it remains the same. If all of that stuff is true, we only have 2 options, success or failure, they're independent and the probability of success remains the same, we can use this formula for our probabilities. We want R out of N trials whoops, wrong color. R out of N, we'll say R out of N successes with a probability of success of P. So P stands for the probability we're successful. It's going to be a combination, just like with the baseball problem, to account for all the different orderings of those R successes. N, out of the N trials, we want R successes. Then we multiply by the probability of success raised to the R power, because we want to have R of those successes. Then we're going to have what's called Q to the N minus R, where Q is the probability of failure. So basically, we are looking at all the different orders times all the different successes times all the different failures. This formula is going to be the key formula that we're going to be using today. So it's a good one to commit to memory, or at least understand where it comes from. If you understand we're looking at the order times the successes times the failures, that formula falls out pretty quickly. So let's try a few examples and see if we can use this formula to find some probabilities. Starting with a factory that finds 2% of its widgets are defective. Run out of space here. What is the probability that a sample of 150 widgets has exactly 3 defective? So, what are we calling success here? Success we're calling a defective widget. So, looking at the defective widgets, our combination is going to account for all the different orderings of these defective widgets. There are 150 widgets. We're going to choose 3 of them to be defective. For the number of successes, there's a probability of 2% that we are defective, so that's 0.02 to the 3rd power, because we want to have 3 defective parts. What's the probability of failure? Well, if success is 2%, failure would be the opposite of that, which is 98%. 100% minus 2% equals 98%. So failure would be 0.98. And how many failures do we want? Well, if there's 3 successes out of 150, there's going to be 147 left to be defective. And we get that by subtracting n minus r. So now we just have to go to our calculator, which has to move to the other side again. So we'll type in 150, go over to combination, 150 choose 3 times 0.02 to the 3rd power, getting out of the exponent, times 0.98 to the 147th power. Enter. And we see we have a probability of 0.2263. 0.2263. Almost a 23% probability that 3 of the 150 will be defective. Let's try another one. Let's say a drug has a side effect that occurs in 1 out of every 30 who take it. What is the probability that out of 8 people, 1 experiences the side effect. So just being really clear, what are we defining as success in this problem? What we're interested in, what we're looking at, is the side effect. So that is considered a success for the sake of this problem. So we're going to do a combination to account for all the different orderings of this side effect. There are 8 people. We're going to choose 1 of them to experience the effects. The probability of having the effect is, we know it happens in 1 out of every 30. So we're going to say the probability is 1 out of 30. And we want that to happen to 1 person. The probability of failure would be the complement of this, where we can take 1 minus 1 out of 30. You might make a common denominator, 30 out of 30. You can see there's 29 out of 30 is the probability. You probably could have done that in your head. 29 out of 30 is the probability of failure. And we want that to happen to all but the 1. So 8 minus 1, 7 people. So we've got 8 choose 1 times 1 over 30 to the first power times 29 over 30 to the 7th power. 8, math, down to choose 1, times, with fractions we're going to have to put them in parentheses for our calculator, 1 out of 30, raised to the first power, times, putting the other fraction in parentheses also, 29 out of 30, raised to the 7th power. We've got a 0.2103. 0.2103 is the probability that 1 out of the next 8 people who take this drug are going to experience the negative side effects. Another variation of this problem, though, is going to be not that we're interested in exactly 1 person, but you'll see we're interested in kind of a range of people. Maybe at most 2 people will experience the side effect, or less than 7 will experience or will be found defective. And so to do that, it's basically going to become a union problem where we want 1 or 2 or 3 or 0. So for example, when calling the IRS, one gets a busy signal, (62% of the time). What is the probability that out of 5 calls, less than 2 receive a busy signal? Making sure we know exactly what we're asking here, less than 2. That means we want to know the probability that there is 1 or 0, less than 2. It's also important to note that these are mutually exclusive. You're not going to have one receive a busy signal and none receive a busy signal at the same time. They're mutually exclusive. There's no overlap. So basically what we can do is we will look at the probability that 1 gets a busy signal and add it to the probability that none get a busy signal. So let's take a look at doing that. We're going to have 2 combinations here. First, with 1, we're looking at 5 calls. We're going to choose 1 of them to be busy. The probability that it's busy is 0.62, and we want that to happen once. The probability that it's not busy is going to be the complement of this. 1 minus 0.62 is 0.38. We want that to happen 4 times. The other case that we're considering is that of the 5, we're going to choose 0 to have a busy signal. So the probability of 0.62 is going to happen 0 times, and the probability of failure, 0.38, that's going to happen 5 times. So we've got 2 binomial probabilities to calculate here, and we are going to add them together. So I'll even mark that here. We're going to add them together. So let's show that. 5, math, probability, choose 1 times 0.62 to the first power out of the exponent. Some calculators you have to get out of the exponent. Some calculators you don't. Times 0.38 to the 4th power. And we are going to, getting out of the exponent, add the other combination. 5, math, choose 0 times 0.62 to the 0 power times 0.38 to the 5th power. And when we add those together, we get a probability of 0.0726. 0.0726. That is the probability that less than 2 are going to receive a busy signal. So that's kind of how we can handle the OR. We add the individual probabilities together. I'm going to do a little variation on a theme, though. What if we have a certain marketing strategy? Maybe it's our Facebook marketing page, and we find that this marketing strategy is successful with 12% of views. In other words, 12% of people who look at our banner on Facebook are clicking on the banner, getting to our web page. We're going to try and sell to them 12% of the time. So what is the probability that out of 13 customers, more than 2 click the banner? What are we talking about here? Well, we want the probability of more than 2. So this is the probability of 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, or 12, or 13. You can kind of see where this is going to become a nightmare to work out. They are mutually exclusive, so we will just be able to add the probabilities, but we are going to have to add a lot of probabilities. 11 probabilities to be exact. Maybe there's a better way here. If the straightforward way is too difficult, I like to consider the complement, where we will take 1 minus the probability of the opposite situation. The opposite of more than 2 is 2 or less. 2 or 1 or 0. Don't forget about 0. That's the one people tend to forget. 2 or 1 or 0. And then we only have to actually calculate 3 of the binomial probabilities, and that might be a little nicer. So let's do that. We're going to do 1 minus Probably should do it in gray to stay consistent. 1 minus, and then we're going to have 3 of these probabilities. Combination. There are 13 customers. We're going to choose 2 of them. We are successful 12% of the time, and we want that to happen twice. We fail, then the opposite of 12% is 88%, 0.88. That's going to happen 11 times, 13 minus 2. And then we're going to keep subtracting. This subtraction does not just refer to the first probability. It's going to subtract the 2, subtract the 1, subtract the 0. Make sure we subtract all these probabilities off. So 13, this time we're going to choose 1 of them to be successful. Success has a probability of 12%. We want that to happen once. Failure has a probability of 88%. We want that to happen 12 times. Minus, also subtracting out the 13 with choosing 0 of them to buy the product. Probability of 12%, we want that to happen 0 times. Probability of 88%, 0.88, we want that to happen 13 times. 13 minus 0. And this is a little more manageable on the calculator. Still a bunch of button clicking, but not too bad. 1, and we're going to subtract each of the probabilities in the complement. 13, math, over to combination. Choose 2 times 0.12 to the second power times 0.88 to the 11th power minus, move the calculator over so we can see it, 13, choose 1 times 0.12 to the first power times 0.88 to the 12th power minus the third probability, which is 13, choose 0 times 0.12 to the 0 times 0.88. Whoops, did not get out of the exponent. Make sure you get out of the exponent. Delete all this off. There we go. Times 0.88 to the 13th power. Enter. The probability is 0.1985. 0.1985. That is the probability that out of 13 customers, more than 2 are going to click the banner and go to our web page. And that's really all there is to binomial probabilities. It's this one simple formula used over and over again. We multiply the order times the successes times the failures. Take a look at your homework assignment, give these a good practice, come to class with questions, and we will see you then.